Go ahead.
All right, welcome everyone to this week's GES Department Seminar. It'll be my pleasure to introduce today's speaker, which is Dr. Ming Lee. Dr. Lee is a professor at the University of Maryland Center for Environmental Science. He obtained his bachelor's in engineering from Hohai University in China before going on to receive his doctorate in philosophy from the University of Oxford in the United Kingdom. Over his distinguished career, Dr. Lee has created a wealth of publications on a multitude of topics in oceanography, including estuarine and coastal dynamics, sea level rise, storm surge, air-sea interaction, and turbulent mixing processes. Most recently, his focus has been on regional impacts of climate change and extreme weather events on estuaries and coastal oceans. And just this year has published articles for Earth and Space Science, the Journal of Geography Research in Oceans, and the Annual Review of Marine Science. Today's talk is titled Fighting Surging Seas in a Changing Climate, Defending Coastlines at All Costs, or Strategic Retreat to the High Ground. And when Dr. Lee is ready and his audio is working, you can turn it over to him.
Yeah,
yes, we can see it.
I can see it, yeah.
All right, excellent. So now you just tell me when,
Yeah.
and I'm going to rely on the graduate students to take care of the chat and anything else, since I'm going to be managing this. So you just tell me when to advance.
Yeah. The next slide, please.
Whoops.
Okay. I only see not the whole screen, but I hope everybody else can see the whole screen.
Oh, wait, let me make that a little smaller then. How's that? No, it's still a little too big. How's that?
Yeah, that's good. That's good. Okay. Again, my apologies for this technology mishap. So the bottom right diagram shows the global mean temperature from 1850 to 2020. As you can see that in the later half of the 19th century, beginning of the 20th century, there's not much change in temperature. But since then, the temperature has steadily increases. Over the last 1.5 century, the temperature has increased by about 1.5 degrees Celsius. If you look at the top left diagram here, the global mean sea level, this has a little bit shorter record from 1900 to 2000. As you can see that over this century, the mean sea level has increased by about 20 centimeters. But you notice that earlier in the 20th century, it only increased at a rate of about 0.6 millimeters per year and accelerates in mid-1950s to 80s. In more recent decades, it increased at a much faster rate, between 3 and 4 millimeters per year. So how do those translate into sea level rise in Chesapeake Bay? Next slide, please. So here we look at the long-term sea level record at 10 tidal gauge stations in Chesapeake Bay. The 5 in the bottom here, the lowest one is from the Hampton Road near Norfolk. The top one is from Baltimore, where most of you are. Actually, Baltimore has a longer record. As you can see, in all those tidal gauge stations, all the mean sea level trending upward. So, in fact, that if you can, you cannot see the numbers, but it has risen at a rate about 3 to 5 millimeters a year over this last century. So this is about twice as much as the global mean average, which is about 2 millimeters a year. So the reason is that because the land we're sitting on is sinking. It's part of the glacial isostatic adjustment. Next slide, please. Because this gradual increase in mean sea level, your next high tide is going to be higher than your previous high tide. That's why we see more what we call Newsom flooding or high tide flooding. This is a picture of a Newsom flooding on April 30, 2014 in downtown Annapolis. It's about 20 to 30 centimeters water. It doesn't probably destroy a lot of buildings, but it closes businesses. Next slide, please. This is another picture in downtown Baltimore. Again, high tide flooding, calm day, no storm. Next slide, please. These are some of the Houston flooding we see on this is Shore area. This is on Fishville and Southville where I am. In fact, I drive my son to school on this street, and you know when the school is open. So sometimes I have to look at the tidal table in order to avoid driving on this flooded road. Next slide, please. So, in order to project or predict kind of tidal flooding we will get in the future, so you probably assume that we just take the mean sea level rise plus the high tide that we're getting now. And you probably have a good reason to believe that because the tides are generated by the gravitational force due to the moon and the sun. But that's not the tide we're seeing in bays like Chesapeake Bay. It's not directly generated by the gravitational force of the moon or sun. They're actually coming from deep ocean as a tidal wave. When the tidal wave comes into a shallow water like Chesapeake Bay, and how it propagates, how its amplitude changes depending on the water depth, depending on the coastline. So if sea level rise increase the water depth, it's going to change the tidal range. If the navigation channel deepening, dredging, make the water depth deeper in that navigation channel, it could change the tidal amplitude. Here is a diagram that looks at the tidal range on the east, I think it's mostly on the east coast of the United States, from about 1850 to about 2010. As you can see that a lot of places have this 19 years fluctuation. That's correspond to the nodal tidal cycle. That's something to do with the orbit of the moon. And last time we had this such high tide was in 2006, and we're due to another one in about 2 or 3 years. Also, you'll notice that in other places like Washington, D.C. and Norfolk, Virginia, the tidal range and actually decreased gradually over the last 100 years. In other places like Philadelphia or Albany, New York, or Wilmington, North Carolina, you will see some very dramatic increases in tidal range in the 20th century. For example, in Philadelphia, from 1900 to about 1950, the tidal range actually increased from about 1.5 meters to about 2 meters, a huge change. This is believed to be associated with channel dredging that make water deeper, and I will explain that more later in our model analysis. The same story in Albany, New York, and Wilmington, North Carolina. So what you do with channel dredging, and it's going to affect the tides. And you also notice that in Boston, Massachusetts, the tidal range, some reason actually decreased, but also there was some channel dredging and shoreline hardening. And but there, for big reason, we don't quite understand the tidal range decreased a little bit toward later half of the 19th century. Again, so this tells us that if you want to look at the high tide flooding in the future climate, not only we have to look at the increase in the mean sea level, but also consider how those tidal range change over time. Next slide, please. In addition to high tide flooding, occasionally we're going to hit by a storm, which have a lot more flooding. And like, in Chesapeake Bay, Hurricane Isabel in 2003. Here I show a picture, a satellite image of hurricanes on September 19, this year. As you can see that there's at least 3 storms on the same day. So there's Tropical Storm Beta that's moving toward landfall. There's Hurricane Teddy in the North Atlantic, and the Tropical Storm Wilford in the further out. And this extra Hurricane Category 2 Polar also will emerge as another storm. Next slide, please. So, and also in addition, in fact, that this year we're gonna hit record. It's like 19 named storms, so we have to run out of the names for these storms. Another thing we're getting in the storms is that we're going to have more west storms like Hurricane Harvey. This probably have a lot of implications for places like Baltimore. And so during Hurricane Harvey, which hit Houston area in 2017, there's a few interesting things. One is that it was a Category 1 storm while in the Gulf of Mexico. It's actually intensified to a Category 3 storm once you approach in the shore, which is pretty unusual. Then there's a lot of rain, a lot of precipitation. So in some places, it received over 60 inches of rain over 2 or 3 day periods. And another thing is that the storm hang around for 2 or 3 days instead of moving away from the area. So that this slow forward propagation speed and heavy precipitation are believed to be associated with climate change. Imagine places like Baltimore has been, suspected for those flash flood flooding, and you have that heavy rainfall together with storm surge. You can have attacks on both sides. Next slide, please. So another storm that hitting close at home is Hurricane Sandy in 2012. It generated extended flooding in New York City, in New Jersey, in Connecticut, those three states, and a lot of subways flooding. It created economic damage of about $19 billion, direct damage, another $35 billion, $19 billion, another $35 billion in repair. And in fact, also Hurricane Sandy also hit Eastern Shore of Maryland, the Bristol. Is a picture of the flooding. About 700 homes were flooded in Bristol during Hurricane Sandy. Next slide, please. Yeah, so people have started to look at the historic trend of hurricanes. This is a synthesis put together by the in the panel IPCC and World Meteorological Organization that was published last year. They look at the number of hurricanes in the North Atlantic, and the green line is the reported total number of hurricanes in the North Atlantic from 1880 to about 2010. And it is you might think that this have an upward trend, but people believe that in earlier days that hurricanes, while they're in the open ocean, was underreported. So that's a corrected number of hurricanes. So you cannot say that there's a lot of year-to-year differences, but apparently there's no longer long-term trend in the increase in the number of hurricanes. And this bottom number shows here, a figure shows the number of hurricanes that went landfall on the United States. So this year will go way up, and so it's very 2020 is a very active year. Although there's no apparent long-term trend in the frequency of the hurricanes, there's definitely a trend in the what we call pole dissipation index. That's a great measure of the frequency, intensity, and duration of the hurricane wind. And you see that clearly from 1980s that pole dissipation index has increases. And that tracks the sea surface temperature over the North Atlantic. So as you imagine that the hurricane gets its energy, its power from there's a heat release from the ocean surface. The warmer the ocean it can release more energy to fuel the hurricanes. So they actually try to get an expert group to come up with a consensus or synthesis of the historic trend. This is what they agree. So 90% people agree that there is detectable increase in the global average hurricane, and especially hurricane becomes stronger. And this is related to climate change. And there's definitely an increase. Everyone agrees that the Category 4 or Category 5 storm, they're increasing not only in the North Atlantic, but in global oceans. and it's also related to climate change. Another thing that's also clear in the historic analysis is that there will be going to be more Harvey-like storms with extreme precipitation events, and it's also related to climate change. Next slide, please. So, how does those stronger storms translate into sea level extremes? People have looked at the long-term sea level record at a number of tidal gauge stations around the world. You cannot see those station numbers in the slides, but they're mostly in North America, in Europe, some in Australia, and these are the reddish band shows that the sea level higher than the long-term average sea level extremes. The blues are lower than that, and you can see that they're sort of decades of higher than normal extreme sea level and decades of lower extreme level. But they're all also coherent over time. So there's some regional basin scale changes of sea level extremes over the past 100 years, 50 years. But there's no clear indication that there's an increasing trend yet. Next slide, please. So we're looking into the future. What kind of storm we're going to get? This is again from that synthesis analysis and a paper appeared in this year. They were saying that if you look at this is global projections, if you look at the hurricane frequency and this is the median projection, actually there's some reduction in hurricane frequency, and this is because that in a warm climate, the wind shear in the upper atmosphere tend to decreases, and that seems to be to increases that tend to make it harder for hurricane to form. So the frequency of the total number of hurricanes may decrease in a warming climate. This is look at mid or late 21st century, but the number of intense storm, category 4 and 5 storm, would increase. Also, they look at the intensity. Definitely, you see that increase in intensity, but definitely you will see that the precipitation rate is going to increase. And if you look at the North Atlantic here, it's clear we're going to see more category 4 and 5 storms and more storms with heavy precipitation, like the Hurricane Harvey. Next slide, please. So how are we going to respond to this stronger storm surge, sea level rise, maybe changing tide? Are we going to build seawalls, like the top diagram here, or levees? Or are we going to use some natural-based system like salt marsh, seagrasses, or consider some adaptation strategies like relocation to high ground? Next slide, please. So we undertake a couple of modeling studies. So to look at how sea level rise and coastline management affect. First, look at the tides first in Chesapeake Bay and Delaware Bay. As you can see that in Chesapeake Bay, most of the low-lying areas are in my back road, on the eastern shore of America. Those are the area where it's less than 1 meter high or 3 feet high. Most of the low-lying area on the eastern shore. In Delaware Bay, it's on the kind of fringes of the mid and lower mid part of the Delaware Bay. So what we want to study in this is that we assume that sea level is going to rise by about a meter by the end of the 21st century. We want to look at also how we manage the coastline would affect this tidal response. Either we consider very simple scenarios. One is where that we put seawalls everywhere, so at the current coastline, so the water will not be allowed to flood. Or another thing, we just do adaptation. We just let low-lying areas to be flooded. So we call soft shoreline. They put seawalls, we call that hard shoreline. And then we compare the tidal response in Chesapeake Bay and Delaware Bay. using, we construct a numerical model that cover the Mid-Atlantic Bight as well as the two estuaries. Next slide, please. So this is the model predictions. This is the present day tides in Chesapeake Bay. You have a highest tide at the mouth about 1 meter, and then decrease quite rapidly to about in the lower bay because of that strong shallow water bottom friction, and reach about 0.3 or 4 meters in the mid bay here, and ramp out a little bit because the tidal wave gets refracted from upstream to in Baltimore, and you're higher than in Annapolis. And so in Delaware Bay, actually it's different. So you have a tidal range about 1 meter, 1.2 meter at the mouth, and then gradually increase because of this coastline conversions. You basically squeeze the tidal wave into a narrow area so that the tidal range actually increases to about 2.5 meters by the time you get to Philadelphia. We actually validate this model against observation. The model does a very good job, about 95% or more accurate than that, in a smaller prediction. The question is that if we have zero rise, 1 meter zero rise, have soft shoreline scenarios, how are the tidal range going to change? So here is in Chesapeake Bay. You can see that the tidal range in the lower Chesapeake Bay actually increases somewhat by a few centimeters, but in the middle bay and upper bay, it decreased by about 8 centimeters. On the other hand, if you put hard shoreline, if you do not allow the water to go spill over those seawalls, you get a little bit of reduction in the lower bay, but you have tidal range in mid-upper part of the Chesapeake Bay increased by up to about 8 centimeters. Similar story in Delaware Bay. If you allow the water to be flooded and low-lying area to be flooded, then you get a reduction of the tidal range. If you don't allow it, you get increase of tidal range. And next slide, please. So here, again, the red line corresponds to 1 meter zero rise. We also consider other zero rise scenarios, like the green line would be 75 meters, and the black line is 50 centimeters. So you can think this black line as mid 25th century, 2050, and red as 2100. And we see that different changes in tidal range. And again, that this is in Chesapeake Bay, it's a little bit reduction in the lower bay, and larger for the hard shoreline scenarios, larger increase up to about 10 centimeters in upper bay. If you do a soft shoreline, little bit of increase in the lower bay, but a reduction of 5 centimeters in the upper bay region. And you can see that similar story under the other zero rise scenarios. In Delaware Bay, actually get a much bigger response, and so 1 meter zero rise in Philadelphia at the African location, you can hard shoreline will increase by about 25 centimeters. If you have a soft shoreline, will decrease by about 25 centimeters. And smaller change, of course, when you have your mean sea level rise is smaller. Sometimes you will say, how big do this matter? Yes, it matters. So if you look at change in mean tidal range by the sea level rise, it's not a small amount. It's about 5 to 10%. In Chesapeake Bay, if you have soft shoreline, it will decrease by about 5%. If you have hard shoreline, increase by 10%. In Delaware Bay, the changes can be minus plus 20 to 25%. So significant change in tidal range due to sea level rise and coastline management. Next slide, please. And we also consider the case that if the tidal range in the North Atlantic changes, they increase by 10% or decrease by 10%, how that's going to affect the tidal range to be paid. Basically, it acts like a damp oscillator, so there will be proportional change, but at a smaller rate. So it's going to have a smaller imprint in Chesapeake Bay. Whatever, if you increase 10% at offshore tide, you can use maybe a 5%. Somewhat interestingly, if you decrease it, it's almost like you get same reduction. So there's a kind of modular damping. Next slide, please. So why is that? The soft shoreline would create a smaller tidal range in the mid and the upper bay. The reason is that when the tides comes in, it dissipate, energy gets dissipated by the bottom friction, and when you allow shallow areas to be flooded, you use additional area for the friction that take out energy, so a lot of energy gets dissipated instead of being sent upstream. If you have hard shorelines, you don't allow that, so a lot of tidal energy gets propagated upstream. And in Delaware Bay, same story. If you have a lot of soft shorelines, you allow the energy to be dissipated at those low-lying areas, so the tidal wave cannot be propagated, not as much as propagate upstream. But if you have hard shorelines, there's less, the water feel less bottom friction, more tides get sent upstream. You guys can hear me okay?
I think they can.
Okay, good, excellent. Okay, next slide, please. Another way to look at this, look at the tidal wave characteristics, the phase lag between the tidal current and tidal sea level. So if it is a 90 degree, if it is a 0 degree, there's no phase lag. That means the tide is a progressive wave. The tide can move forward, like in the lower part of Chesapeake Bay. So the tidal can move forward. The tidal wave can propagate further inward. But in the upper bay, it's close to 90 degrees because the waves are reflected. So if you have a soft shoreline, basically that the phase lag is even lower. So here there's a little reflection here, but with soft shoreline, you basically allow a lot of waves to become more progressive like, so they can fill out sideways. On the other hand, if you have a hard shoreline, you make this more like a standing wave, so that the waves get amplified. Same story here in Delaware Bay. When you have lot of reflection from the side boundaries. If you have these soft shorelines, you can let a lot of things fill the sideways, and so that not much tidal wave get propagate upstream. The opposite is true when you have a hardened shoreline, and then you get more standing wave like, so the wave gonna get amplified. Next slide, please. So this can amount to quite a big difference, between soft shoreline and hard shoreline. So it can be about, in Baltimore, 18% difference in peak water level. In Washington, D.C., 11%. In Philadelphia, it can be 21% of the entire height. So it's not a small difference. So how we manage coastline can mean a big difference in terms of peak tidal height or tidal flooding in the future. So something we need to consider when we manage for flooding in the future climate. Next slide, please. So another thing we did was to look at the storm surge. So the question we try to address is that in Isabel, like storm hit in 2050 when the mean sea level is higher, oceans warmer, and how is that going to affect Chesapeake Bay? So as you know, the Isabel flooded Washington D.C., Baltimore, Annapolis, and the eastern shore of Maryland. Next slide, please. So we developed a regional atmospheric ocean model. The regional atmospheric model is based on weather research forecasting model. It's a triple nested domain, and the field domain covers the east coast of the United States and Atlantic Ocean. The inner domain covers Chesapeake Bay, where we can have fine resolution to wind that can drive the storm surge model. That's the same we use for the tides. Next slide, please. So we consider different climate change scenarios for 2100. So medium emission scenario, high emission scenario, and these are projects change in the sea surface temperature and rate to zero rise. Excuse me. Next slide, please. This is the change in the storm intensity. As you can see that the sea level, minimum sea level pressure increased quite a bit. This is the 2003. This is the open circle of observations, and black line are model predictions. And this is the predicted for future. In 2050, the minimum sea level pressure intensify, lower. Wind is going to be higher. Same with the 2100, you're going to get an even larger drop in the minimum sea level pressure, and to 920, something like that. Maximum wind to about 60 meters per second. Next slide, please. Yeah, so as a result of that, you're going to see a lot more latent heat release into the atmosphere, and that's going to intensify and make the storm more intense. Next slide, please. So as a result, that your storm tide in Chesapeake, in Baltimore, will be much larger, from about 2.2 meters in 2003 to about 2.5 meters in 2050 for soft shoreline scenario, even higher, about 3 meters in the hard shoreline. Much bigger change in the 2100. You know, you're going to get to storm surge tide will increase to about 2.7 meters soft shoreline, but 3.5 meters in hard shoreline scenarios. So much bigger increase when you have soft hard shoreline. Same reason, because you don't allow the water to spill over the low-lying area. You force them to go to the upstream locations like Baltimore and Washington, D.C., where you get much larger increase in the storm surge height. And if you think about it, in 2003 it was 2.2 meters, and this is just surge height. If you add the 1 meter zero rise, that's going to be 4.5 meters. So it's a doubling of peak water in 2100, and due to zero rise and warming. Okay, next slide, please. Yeah, this just shows you that it's happening everywhere, and not only in Baltimore, but all the other places, Annapolis, and other locations in Chesapeake Bay. The difference between hard shoreline and soft shoreline is more pronounced in upper and mid bay locations, because in Norfolk it change a bit, because that's before the coastline management affects the lower bay location. Next slide, please. Yeah, here just shows that what contributes most to the surge height increase. We consider the sea level rise only, or warming only. So just make it simple that what we find is that sea level rapid rise just very simply sea level doesn't change the surge height, but the warming really increase the surge height. Also, the hard shoreline is going to be much higher than the soft shoreline scenario. The surge height is going to be much higher than the on hard shoreline. So shoreline management and warming are two major factors impacting the surge height. Next slide, please. Yeah, so we did some budget analysis of the storm surge to see why there's a big difference between the soft shoreline and hard shoreline. So basically, this is a little messy. Look at the energy of the storm surge, and the primary balance is wind energy input versus the dissipation. But there's also incoming surge, and that provide additional energy. But if you look at the remaining second order balance, go to the next slide, please. You will find that the dissipation and the wind energy input balances, but what's remaining is actually the incoming tidal surge is the biggest term that driving the increases. But if you have soft shorelines, you have this leakage of energy that's coming out from the side boundaries. So if you have this is current 2003, so you have a little bit of energy leaking out from the side boundary right now. And if you have hard shoreline, there's nothing. But in the future climate with zero rise, you're going to have a lot more energy leaking out if you allow low-lying area to be flooded. So this tells us that this sideway leakage of energy can be an important way to reduce the storm surge height in aggregate location like the Baltimore. Next slide, please. This just look at the projected increases in the inundated area due to this category 2 storm like Isabel. And here we don't do any coastline management. We just assume all the low-lying area be flooded. This is the area that be flooded 2003, 2050, ICP 4.5, 8.5, 2100 for 2 climate change scenario. So 2003 flooded about 1900 kilometer square land. But in 2100, it's going to be almost 60 or 70% larger. So there's going to be significantly more places be flooded. You all notice that, like places on Western Shore near the coastline will be flooded in the future climate due to this kind of category 2 storm. In 2003, it was much more limited. So there will be great expansion of inundated area in the future. Next slide, please. Yeah, this is just look at eastern shore of Dorchester County. Here actually it's interesting because there's a steep change of topography. So there's not much extension in the inundated area. It's more of increasing inundated depths. Next slide, please. And this is Isabel. Look at inundation map of Baltimore in Isabel. So only the inner harbor area and Little Italy area was flooded. But for 250, 2100, there'll be much more extensive area be flooded around downtown Baltimore. Next slide, please. This is look at inundated area. Baltimore was about, during 2003, was about 2.5 kilometers square. But 2050 would be 3 times. By 2100, it would be about, would be 10 kilometers square, 5 times larger. Next slide, please. Then we just basically using the damage function from the FEMA, look at the cost of the potential cost, property loss. So there will be like 3 to 4 increases of property loss in Baltimore in 2050, maybe 5 to 6 times in 2100. Okay, next slide, please. So then we just do some, how do we protect places like Chesapeake Bay from future flooding? Are we going to do flood walls? Is that the estimate of the cost here? Chesapeake Bay have a very long shoreline. So that was going to be worked out to be $327 billion for seawalls, about almost $100 million for levees. And even look at a place like Dorchester County has 1,500 miles miles of coastline. It will be tremendous cost for this rural county. Next slide, please. And then you might think we want to do some nature-based system like wetland restoration, seagrass restoration, or the reef. They are cost less. They also engineer the system, but also there's some cool benefits in the system. It's not an inexpensive option either. Next slide, please. Maybe we can think about a storm barrier, constructing a barrier at the Bay Bridge Tunnel. So I look at the cost of building a new Bedford hurricane barrier, and it would translate to about $3.4 billion in a storm surge barrier at the north of Chesapeake Bay. But there's some side effects, into saltwater intrusion, long racism time, affect, fish migration, a lot of other things that we need to evaluate. Next slide, please. So then this brings me to this adaptation strategy. Maybe we should think about, instead of trying to defend the coastline at those very larger costs, maybe think about moving some communities away from those rural areas, compensate for their cost, and it's already happening in Louisiana already. Yeah, last slide, please. So, to conclude, in summary, to the sea level rise and intensify storm in a changing climate, they are global phenomenon, but it's not something we cannot do anything about it. So, how we manage a coastline in a bay like Chesapeake Bay can affect what kind of storm surge or tide we're getting. And, the tidal range in upper Chesapeake Bay can increase or decrease by 10 centimeters, depending how we manage coastline. And peak water level in Baltimore, like Isabel storm, can increase from 2.2 meters to 3.7 meters in 2100. If we higher the shoreline, it will increase further by about 0.8 meters. So again, how we manage coastline matters. The physics behind this is that any dissipation over shallow flood area really make a difference. They can take punch out of those tidal waves, storm surge, and really help the upstream location. But then, it's a hard sell for people like the shore, where, you ask them to migrate to high ground and flood their home, leave their homes, and to save Baltimore, Washington, D.C. So the community in Chesapeake have to discuss this and think whether the location is a viable adaptation strategy. It's not just involve physical science, but also involve social science, people, community coming together. Last slide, please. I just want to acknowledge my student, Foster, and Tiger is working with me on this funded project. Again, I apologize for this mishap in the web accident. I'm happy to take some questions.
So I think we are actually not even at 1 o'clock yet. I realize some people may have to leave at 1 sharp. So if you're in that situation, please feel free to do that. But I think we can take some questions, and then some people who are interested in staying behind for sort of a virtual lunch. I will create a Zoom. Meeting for that, for those who want to do that, and I'll put the link in the chat once we're done with the questions. So for those who want to do that, I'll just put the link in the chat before we close this meeting. But I think if we have people who want to ask questions, this is a good time. So thank you. So if you have a question, I think you can just unmute yourself and ask the question. Well, I'm going to ask one while we're waiting for other people to think about it. And actually, I was going to ask this over lunch, but I'll ask it now. So there's actually a meeting of the management board for the Chesapeake Bay program tomorrow, and they're actually going to be talking about climate change adaptation strategy. Have they been consulting with you about some of these issues in terms of strategies for shoreline management?
No, I'm not aware of that particular meeting, but I've been talking to people Andy and other people, but I'm not aware of it. With Linda, I'm in contact with him.
Yeah.
I'm not aware of this particular meeting.
Yeah, it seems like what you're doing is very germane to what they're talking about, even though it's not all about coastal sea level rise, but certainly parts of it are. So I can send you the documents that I just got from the. I'm just going to attend part of that meeting. Upal.
Yeah, this was a great presentation, Dr. Lee. Really, I learned a lot. And I have a quick question. I may have missed a part of your presentation. You talked about adaptation and how maybe allowing flooding to happen in some of the coastline areas may be a way to think about it. To what extent is that kind of adaptation of allowing flooding to take out some of that energy and flow is being coordinated or needs to be coordinated with flooding that one may allow maybe upstream in the rivers to happen at a strategic time?
Yeah, I'm not here. I'm more talking about this, not rivers, but the I'm looking at where the low-lying areas surrounding Chesapeake Bay. It happened to be like on the eastern shore. Southern half of Dutchess County is below 1 meter sea level rise. So if you have a 1 meter sea level rise, you can flood those areas. Even though the additional area is small compared to the surface area of Chesapeake Bay, it seems to be, at least our model results shows that additional area seem to be able to take out a lot of energy out of those tidal waves and storm surge.
Thank you. I was recently reading a report by the U.S. Army Corps of Engineers, and it's got a very interesting title. It's called Room for the River. And what it talks about is allowing some of the flooding, and they're basically looking at the Mississippi and allowing the Mississippi to flood in areas that we have in the past not allowed to flood is an adaptation that we have to start thinking very seriously about.
Yeah, I think adaptation and how people move away from home it's a very hard competition. Show. I never bring this topic with my name. People see their home is value and other things. So, but we have so many miles. Those, it just realistically too expensive. Yeah, it's a hard conversation that we have to talk about. The community has to talk about.
Thank you.
Okay, does anybody else have questions?
I had one quick question, unless people were trying to leave or anything.
Well, people can leave if they wish, but there's no reason not to ask.
Yep. So this might be more of a land subsidence question, but I remember hearing about some things during Hurricane Harvey, how the area around Houston had actually, there had been a noticeable amount of land subsidence due to the weight of the water on top of the region. And I was wondering if similar things might start happening in parts of Maryland and what effects that might have on further tidal change.
It could be. I think that the main thing that's driving the less subsidence in Maryland is that the glacial anesthetic adjustment as part of the ice retreat during the glacial age. But there's also additional factors such as groundwater extraction. Like in Norfolk, they got very large subsidence rate because of the groundwater extraction. I know groundwater extraction is not only in that area, other places they have that. So the subsidence rate is not uniform to the big bay. So there's probably up to about 10 centimeter differences among different places. And looking into the future, that still probably the spatial homogeneity in the subsidence rate is still be smaller than the sea rise rate. We have up to 1 meter, 1 meter increase in global mean sea level. That so the that change is much bigger than the subsidence rate in the 21st century. In the 20th century, it's probably half is global mean sea rise, half subsidence. But in the 21st century, I think most of it will come from the ocean. Is zero, zero rise.
Okay, anybody else have questions? I am posting a link to a Zoom meeting in the chat, so if anybody wants to join us for virtual lunch, seeing as the only way we can communicate with Dr. Lee right now is through my cell phone, he can use Zoom and we can all come in. So some of you can indicate an interest in that if you want to do that. I think we'll take a break for a few minutes so people can grab their lunch, and then I'll open up that Zoom meeting as soon as I close this call. So